All right, so for we'll call this lecture 21, and I'm booting everything up to 20, 21, 22 in order to make the flow a little bit better, making it clear that it is section 2. So for lecture 21, we're going to be talking about anisotropy. So just a real quick review from the last lecture, lecture 21, where we said we could break down things into generalized Hooke's law, where we have a strain field is equal to some material property matrix times some stress field. And we did this for the relatively simple case of normal strains and normal stresses. But we can actually expand this even further out to, let's make that a little bit clearer, to both normal and shear stresses in the same matrix. So the convention on the shear stresses is a little bit odd, I will admit. Okay, this would be our vector, and I've never really understood why they put things in this particular order. Okay, the normal strains makes a lot of sense. You go X, Y, Z. For some reason, with our shear strains, we start with, and I have to look it up every time, we start with YZ, then XZ, and then XY. I'm not sure where that convention came from, but that is the convention that we generally work with when we are assigning these things in vector form. Okay, so if I wrote, this is a 3x3 relationship, where this is a 3x3 matrix. And this is the 6x6 relationship here. So here, the material property matrix is 6x6. And I have a stress vector here as well. Okay. All right, so for generalized Hooke's law, we can either write the individual equations like we started with in the last class, or we can switch it into a form which is generalized in the matrix form, where you have a 3x3 sort of relationship here, or a 6x6 relationship here. All right, so why does that matter? Well, it turns out that we can simplify a lot of our material properties by using generalized Hooke's law. All right, so up until now, we've been dealing with isotropic materials, and we'll go through this matrix, this material property matrix for isotropic materials, and maybe I'll convince you that this is relatively useful. All right, so isotropic. Well, what is meant by isotropic materials? Well, first we'll start off with our material property matrix S. All right, so the items that appear in the material property matrix, they're a function of the elastic modulus and the Poisson's ratio, and we can even say the shear modulus. All right, but it actually simplifies down to it being just a function of the elastic modulus and Poisson's ratio, and this is because the shear modulus G for an isotropic material is approximately equal to the elastic modulus divided by 2, 1 plus Poisson's ratio. Okay, and it just so happens that in a lot of isotropic materials, the Poisson's ratio is roughly equal to 0.5, and so if we take this and solve it out, we would get G is equal to E over 2. All right, 2 times 1.5. Sorry about that. Right, which would basically be the elastic modulus over 3. And so sometimes you will see this sort of relationship. Nonetheless, there's generally some relationship between the elastic modulus and shear modulus that allows us to simplify the material property matrix down to just 2 elements. All right, this is really convenient because if the material is isotropic, the entire material property matrix can be determined in a single mechanical test. Right? Because in one test, we can calculate the elastic modulus and the Poisson's ratio, and from that we can define the entire material property matrix. All right, so what is the material property matrix for an isotropic solid? Well, all of these are going to be relatively large 6x6 matrices. All right. 1 over e to the x. Oops. We don't need the x here because all of them are the same. 1 over e. 1 over e. Negative Poisson's ratio over e. Negative Poisson's ratio over e. Negative Poisson's ratio over e. Each one of these corners. And then 1 over g down the remainder of the diagonal. And this is a 6x6 matrix. So I'm going to do my best to fill in all the zeros. Alright, there's my 6x6 matrix, and I had to write this note out at the side where G is approximately equal to the elastic modulus divided by 2, 1 plus Poisson's ratio. Alright. And so as long as we know the material is isotropic, and we have the elastic modulus and the Poisson's ratio, and we have this relationship here, we can calculate the strain field in the material for any set of stresses using this relationship here. So what are the criteria for this? The criteria for isotropy. Number 1. The elastic modulus in the x direction must be equal to the elastic modulus in the y direction and the elastic modulus in the z direction. In other words, it doesn't matter whether I'm pulling in the x direction, the y direction, or z direction, or I'm pushing in the x, y, and z. I'm going to have the same response in all directions. Number 2. The Poisson's ratio is the same in all directions. Okay. Again, the Poisson's ratio is independent of direction. That's what both of these are saying. Elastic modulus and Poisson's ratio are independent of direction. And then the third criteria, the same is true for the shear modulus. So we can add the shear modulus in here. All right. And then the fourth criteria, which is going to be important really for all of the anisotropic material property matrices that we talk about today, is that due to symmetry, relationships between normal and shear strains are negligible. All right. What that last one allows us to do is put all these zeros in. Okay, so it's basically saying if I have, I'll go all the way back up to the beginning. All right. If I have some macro scale shear, it's going to cause some shear strain at the elemental level, but it's not going to cause some normal strain at the elemental level. Same thing here. If I have some normal strain, it's not going to be able to cause some shear strain at the elemental level. Okay, that's relatively important. All right, in the sense of it basically allows us to devolve normal strains from shear strains, and basically saying the only relationship between normal and shear is going to be some rotational factor. Right, so this doesn't mean that Moore's circle doesn't apply. It just means that the only thing that's going to relate our normal stresses to our shear stresses is some geometric rotation of the element. They can't actually cause each other through something like a Poisson's effect. All right. So before I move on to the more complex one, this is the thing I want you to remember. This is the thing I want you to jot down on your notes. Okay, what does an isotropic material property matrix look like? Okay, and this is our first material property matrix, this isotropic one. All right, now we're going to move from the simplest one to the most difficult one that we're going to handle in this class, which is the orthotropic material property matrix. All right, so I'm going to do this one maybe in a little bit backwards formation. We're going to talk about the criteria first. It's the most complicated one that we'll deal with in this class because dealing with pure anisotropy is virtually nobody does it. It's just too complex. The most complex we typically deal with is this orthotropic behavior. And here this is saying the elastic modulus in E, or in X direction, is different than the elastic modulus in the Y direction, is different than the elastic modulus in the Z direction. In the same way, the Poisson's ratio for X and Y is not equivalent to the Poisson's ratio in X and Z, is not equivalent to the Poisson's ratio in Y and Z. Okay? And furthermore, X and Y for the shear modulus is not the same as X and Z, and is not the same as Y and Z. We'll come back and revisit these at the end. The one that will still apply is this symmetry effects. Due to symmetry, no relationship, or we'll say, I don't want to say no relationship, we'll say negligible relationship between normal and shear. Strains. Okay, well, I introduced a couple of new terms here. All right, most people don't get too shocked by the elastic modulus in X, the elastic modulus in Y, and the elastic modulus in Z. So if I pull this thing out, I draw a three-dimensional element. Okay, and I call that Y, X, and Z. Is basically saying that the elastic modulus in this direction, let me switch colors to make it a little bit more obvious what I'm doing here. Right, the elastic modulus in this direction is different than the elastic modulus in this direction, and is different than the elastic modulus in this direction. Okay, that's usually people can kind of wrap their head around this. Maybe there's some fiber running in one direction that makes it a little bit stiffer in one direction versus the other, or maybe there's some sort of weave pattern that allows this to occur. All right, it's actually not that hard of a jump mathematically from here to here, but this nomenclature gets people a little twisted up sometimes. Okay, so what does, let me switch back to black, what does new X, Y relate to? Well, it relates to the relationship between, oops, I should have said, the strain in X and the strain in Y. Okay, and what we're not saying here is that strain in X and strain in Y, they're still related. Okay, so we can say that new XY is still equal to new YX, or that we can flip these two around, right, and still end up with relatively the same ratio, just flipped in the other direction. So those things still exist. X and Y have a certain relationship to each other that's described by this Poisson's effect. And X and Z have a certain relationship together that's described by the Poisson's effect for new XZ. And Y and Z have a relationship for each other defined by the Poisson's ratio of new YZ. It's just that we can't tell anything about the relationship between X and Z from the relationship from X and Y, and we can't tell anything about the relationship between X and Z relative to the ratio from Y and Z, right? So we can't really go between these different parameters. They don't really relate to each other anymore, and that's because we have slightly different material properties in each direction. The same sort of thing happens here. Okay, so if we shear it in one different direction, right, so if we shear it like this, or we shear it like this, or we shear it like this, all of it's going to respond slightly different. So usually people are like, how could this possibly occur? So let me pause the video real quick and I'll pull up an image of an orthotropic material. Okay, so let me drag this over into the screen. You should be able to see it. Okay, orthotropic materials are actually pretty common. All right, so what they have is some symmetry that exists amongst the three different axes. So here we can have some symmetry. Actually, let me open that up in Illustrator so I can draw on it. All right, now we're back. Okay. So orthotropic materials possess some symmetry about the different axes. So this is a good example of an orthotropic material. So it has some fibers stacked in different directions, right? So, and they're laid at 90 degrees from each other. So here's a layer with fibers laid in this direction, and then this direction, then again this direction, and then this direction, right? And we're just going to stack these fibers on top of each other, and you'll also notice that there is some sort of symmetry in this direction as well. It's layer, 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 right? So it might be relatively easy to separate the layers from one another, right? So if I pull it in this Z direction, I'm just unstacking the different layers. So I'm going to have some elastic modulus associated with this unstacking of the layers. Now let's go in the Z direction, which is going to be this direction here. Or I'm sorry, the Y direction. Ugh. So if I pulled in the Y direction like this, right, these fibers here, these ones that I'm kind of shading in here, right, they're directly in line with this. So they're going to have a lot of resistance, right? So the fibers lining or aligning with the Y direction will have the primary resistance to stresses in the Y direction, right? And the same way we could have some stress in X, in and out, right? And the fibers aligning in X are going to have some resistance there. Now, if this fiber in X is different than the fiber in Y, then all of a sudden X and Y have different material properties. In the same way, the Poisson's effects for when I'm pulling on a fiber that aligns in the X direction are going to be different than a fiber aligned in the Y direction, and it's going to be different than this unstacking of the different fibers. And so this is the classic you can't push on a rope problem. When you have different fibers being loaded, preferentially with the direction, it's actually really easy to develop these sort of orthotropic material properties. And so they're actually not all that common, right? Or not that uncommon. Orthotropic is actually very, very common, especially in engineering materials. And the classic example of this is carbon reinforced materials. Where you can create material properties for certain axes. All right, so back to generalized Hooke's law. Where does this all apply? All right, we have this material property matrix again. And it's going to be 1 over EX, 1 over EY, 1 over EZ, 1 over GYX, 1 over GZX, and 1 over GXY. Then we're going to have all our different Poisson's ratios, XY over EY, XZ over EZ, YZ over EZ. I know, I fill these in kind of randomly. It's hard to figure out which way to fill them in sometimes. And then YZ over EY. Okay, that's everything. Everything else is zeros because of our symmetry concern. All right, so it does actually end up being simplified because of all these zeros that we get to introduce, even though our material properties aren't necessarily relating to each other all that cleanly, or we don't have that nice reduction that we get from isotropic. All right, so how do you remember which ones of these go in the different locations? All right, so EX is always going to go on bottom in this first column. EY is on bottom in this column. EZ in this column. All right, and then we basically